A disconnecting means at the distribution point is only required for farms that have the conditions listed in National Electrical Code section 547.1. These conditions include firstly, a distribution point that supplies more than one building or structure, secondly, a mobile home park, thirdly, a recreational vehicle park, and fourthly, a commercial agricultural building. The purpose of the disconnecting means is to allow for the safe disconnection of power to all buildings or structures served by the distribution point in the event of an emergency or for maintenance or repairs. A distribution point can be used in installations that are not covered by Article 547. The definition of a distribution point in Article 547 is not specific to farm applications. However, the requirements for disconnecting means at distribution points in farm applications are only applicable in the situations listed in section 547.1. A pole can have a meter with service drops to multiple buildings, even if Article 547 does not apply. In such cases, a disconnect may be present but is not required. If a disconnect is present, it does not require grounding. The wires to and from the meter are typically referred to as meter leads or meter risers. The light on the pole is likely connected to a separate branch circuit that originates from the service panel or a transformer on the pole. The branch circuit protection would be located at the service panel or transformer. The service equipment and service disconnect would be located at the point where the branch circuit originated. Let's delve further into each of these aspects to provide a comprehensive understanding. When considering disconnecting means at distribution points for farms, section 547.1 of the National Electrical Code outlines specific conditions that necessitate such a disconnecting means. These conditions, as previously mentioned, encompass scenarios where a distribution point serves multiple buildings or structures, mobile home parks, recreational vehicle parks, and commercial agricultural buildings. The rationale behind requiring a disconnecting means in these situations is rooted in safety and operational efficiency. In the event of an emergency, such as a fire or electrical fault, or during routine maintenance and repairs, the ability to quickly and safely disconnect power to all connected buildings or structures becomes paramount. This ensures the safety of personnel and prevents further damage to equipment and property. It is important to note that the requirements for disconnecting means at distribution points are specifically tailored to farm applications under the conditions listed in 547.1. While the definition of a distribution point itself is not exclusive to farm applications, the mandatory disconnection requirements are. This means that in non-farm settings, a distribution point can still be utilized, but the need for a disconnecting means is determined by other relevant sections of the National Electrical Code based on the specific circumstances. Regarding poles with meters and service drops, it is indeed permissible to have a pole serving as a metering point with service drops extending to multiple buildings, even if Article 547 does not apply. In such cases, the presence of a disconnect is optional, not mandatory. Moreover, if a disconnect is installed, it is not required to be grounded. This flexibility allows for various configurations to suit the specific needs of the installation. The wires that run to and from the meter, commonly referred to as meter leads or meter risers, play a crucial role in the overall electrical system. These wires carry the electrical current from the service drop to the meter for measurement and then onward to the building or structure being served. Proper sizing and installation of meter leads are essential to ensure accurate metering and prevent voltage drops or overheating. When it comes to lights mounted on utility poles, their power source and protection mechanisms must adhere to electrical code requirements. Typically, these lights are connected to a separate branch circuit that originates either from the service panel of one of the buildings being served or from a transformer located on the pole itself. The branch circuit protection, such as a circuit breaker or fuse, would be situated at the service panel or transformer, providing overcurrent protection for the lighting circuit. The service equipment and service disconnect for the lighting circuit would also be located at the point where the branch circuit originates, ensuring that the light can be safely disconnected from the power source when necessary. In summary, understanding the specific requirements for disconnecting means at distribution points, the applicability of Article 547, the configurations of poles with meters and service drops, and the wiring of pole-mounted lights is crucial for ensuring safe and compliant electrical installations. Always consult the latest edition of the National Electrical Code and local regulations for specific requirements and guidance. Now let's expand on the requirements for disconnecting means at the distribution point for farms as outlined in Section 547.1 of the National Electrical Code. This section is crucial for ensuring the safety and proper operation of electrical systems in agricultural settings. The conditions that necessitate a disconnecting means at the distribution point are very specific, so let's reiterate. Firstly, a distribution point that supplies more than one building or structure requires a disconnecting means. This condition is common in farms where multiple buildings, such as barns, sheds, and workshops, are supplied from a central distribution point. The disconnecting means allows for the entire electrical system to be energized in case of an emergency or for maintenance purposes. Secondly, mobile home parks also require a disconnecting means at the distribution point. Mobile home parks often have a central distribution point that supplies power to multiple mobile homes. A disconnecting means ensures that the power to all mobile homes can be quickly and safely disconnected if needed. Thirdly, recreational vehicle parks fall under the same requirement. Similar to mobile home parks, recreational vehicle parks have a central distribution point that supplies power to multiple recreational vehicles. A disconnecting means provides a means to disconnect power to all recreational vehicles in case of an emergency or for maintenance. Fourthly, commercial agricultural buildings also require a disconnecting means. These buildings, which include structures used for housing livestock, processing agricultural products, or storing equipment, often have complex electrical systems. A disconnecting means allows for the safe disconnection of power to the entire building in case of an emergency or for maintenance. The purpose of the disconnecting means is to provide a way to safely energize the electrical system in case of an emergency, such as a fire, electrical fault, or natural disaster. It also allows for maintenance and repairs to be performed safely, without the risk of electric shock. The disconnecting means should be readily accessible and clearly labeled so that it can be easily located and operated in an emergency. It should also be capable of disconnecting all ungrounded conductors simultaneously. It is important to note that the requirements for disconnecting means at distribution points are specific to farm applications under the conditions listed in Section 547.1. While the definition of a distribution point itself is not exclusive to farm applications, the mandatory disconnection requirements are. This means that in non-farm settings, a distribution point can still be utilized, but the need for a disconnecting means is determined by other relevant sections of the National Electrical Code based on the specific circumstances. Now let's elaborate on the applicability of distribution points in electrical installations. While Article 547 of the National Electrical Code specifically addresses agricultural buildings and their unique electrical requirements, the concept of a distribution point is not limited to farm applications. A distribution point, in general terms, refers to a location where electrical power is distributed to multiple loads of buildings. It serves as a central hub for branching out electrical circuits. The definition of a distribution point in Article 547 is not specific to farm applications. This means that the general concept of a distribution point can be applied to various electrical installations, regardless of whether they fall under the scope of Article 547 or not. However, it is important to distinguish between the general concept of a distribution point and the specific requirements for disconnecting means at distribution points in farm applications. As mentioned earlier, the mandatory disconnection requirements outlined in Article 547 are only applicable in the specific situations listed in Section 547.1. In non-farm settings, the use of a distribution point is still permissible, but the requirements for disconnecting means would be governed by other relevant sections of the National Electrical Code, depending on the specific application and the characteristics of the electrical system. For example, in a commercial building, a distribution panel may serve as a distribution point for multiple branch circuits. The requirements for disconnecting means of this distribution pile will be found in Article 230 of the National Electrical Code, which covers service entrances and equipment. Similarly, in an industrial facility, a motor control center may serve as a distribution point for multiple motor circuits. The requirements for disconnecting means at the motor control center would be found in Article 430 of the National Electrical Code, which covers motors, motor circuits, and controllers. In summary, the concept of a distribution point is not limited to farm applications, and it can be used in various electrical installations. However, the specific requirements for disconnecting means at distribution points are determined by the relevant sections of the National Electrical Code based on their application and the characteristics of the electrical system. Now, let's discuss the scenario of a pole with a meter and service drop supplying power to multiple buildings. As previously mentioned, it is permissible to have such a configuration, even if Article 547 does not apply. In this scenario, the pole serves as the point of connection to the utility's service drop, and the meter measures the total amount of electrical energy consumed by all the buildings being served. Service drops then extend from the pole to each individual building, providing them with electrical power. In such cases, a disconnect may be present on the pole, but it is not required by the National Electrical Code. The decision to install a disconnect is often based on factors such as convenience, safety, and the specific requirements of the local utility. If a disconnect is present on the pole, it does not require grounding. This is because the disconnect is typically located on the supply side of the service, and the grounding requirements for service equipment are different from those for other types of equipment. The grounding requirements for service equipment are outlined in Article 250 of the National Electrical Code. It is important to note that while a disconnect on the pole is not required, each individual building being served by the service drops must have its own service disconnect. This service disconnect must comply with the requirements of Article 230 of the National Electrical Code. The service disconnect provides a means to disconnect all the power to the building in case of an emergency or for maintenance purposes. In summary, a pole with a meter and service drop supplying power to multiple buildings is a permissible configuration, even if Article 547 does not apply. A disconnect on the pole is not required, and if present, it does not need to be grounded. However, each individual building must have its own service disconnect that complies with the requirements of Article 230 of the National Electrical Code. Now, let's clarify the terminology for the wires that run to and from the meter in an electrical service. These wires are commonly referred to as meter leads or meter risers. Meter leads are the conductors that connect the service drop or service lateral to the meter. They carry the incoming electrical power from the utility to the meter for measurement. Meter risers are the conductors that connect the meter to the service equipment inside the building or structure. They carry the metered electrical power from the meter to the service equipment for distribution to the various circuits within the building. Meter leads and meter risers are typically sized based on the ampacity of the service and the voltage drop requirements of the National Electrical Code. The ampacity of the conductors must be sufficient to carry the maximum expected load without overheating. The voltage drop must be kept within acceptable limits to ensure that the equipment being served receives adequate voltage. The installation of meter leads and meter risers must comply with the requirements of Article 310 of the National Electrical Code, which covers conductors for general wiring. This article specifies the types of conductors that are permitted, the methods of installation, and the requirements for protecting conductors from physical damage. It is important to ensure that meter leads and meter risers are properly installed and maintained to prevent electrical hazards and ensure accurate metering. Damaged or deteriorated conductors can lead to voltage drops, overheating, and even electrical fires. In summary, the wires that run to and from the meter are commonly referred to as meter leads or meter risers. These conductors carry the electrical power from the service drop or service lateral to the meter and from the meter to the service equipment. Proper sizing, installation, and maintenance of meter leads and meter risers are essential for safe and reliable electrical service. Finally, let's address the scenario of a light mounted on a utility pole and how it meets the requirements of the National Electrical Code. Typically, a light on a utility pole is powered by a separate branch circuit that originates from either the service panel of one of the buildings being served or from a transformer located in the pole itself. The branch circuit protection, such as a circuit breaker or fuse, is located at the service panel or transformer, providing overcurrent protection for the lighting circuit. The service equipment and service disconnect for the lighting circuit are also located at the point where the branch circuit originates. This means that if the branch circuit originates from the service panel of a building, the service equipment and service disconnect for the lighting circuit would be located at the service panel. If the branch circuit originates from a transformer on the pole, the service equipment and service disconnect for the lighting circuit would be located at the transformer. The wiring for the lighting circuit must comply with the requirements of Article 410 of the National Electrical Code, which covers luminaires, lamp holders, and lamps. This article specifies the types of wiring methods that are permitted, the requirements for grounding, and the requirements for protecting conductors from physical damage. It is important to ensure that the lighting circuit is properly installed and maintained to prevent electrical hazards and ensure reliable operation. Damaged or deteriorated wiring can lead to short circuits, ground faults, and even electrical fires. In addition to the National Electrical Code requirements, local utility companies often have their own specific requirements for pole-mounted lights. These requirements may include specifications for the type of luminaire, the mounting height, and the control method. It is important to consult with the local utility company to ensure that the pole-mounted light complies with all applicable requirements. In summary, a light on a utility pole is typically powered by a separate branch circuit that originates from either the service panel of a building or from a transformer on the pole. The branch circuit protection, service equipment, and service disconnect are located at the point where the branch circuit originates. The wiring for the lighting circuit must comply with the requirements of Article 410 of the National Electrical Code, and the installation must also meet the requirements of the local utility company. Considering the electrical branch circuit, let us examine branch circuits and overcurrent protection in detail. Branch circuits are the lifeblood of any electrical distribution system. They are the circuits that extend from the final overcurrent protection device to the outlets, lighting fixtures, and other electrical loads throughout a building. Overcurrent protection is essential for protecting branch circuits from damage caused by excessive current flow. Overcurrent can result from short circuits, ground faults, or overloads. Short circuits occur when there is an unintentional connection between two or more conductors of different potential. Ground faults occur when there is an unintentional connection between a conductor and ground. Overloads occur when the current flowing through a circuit exceeds the ampacity of the conductors. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when an overcurrent condition occurs. Circuit breakers are electromechanical devices that automatically trip and open the circuit when an overcurrent is detected. Fuses are one-time use devices that melt and open the circuit when an overcurrent is detected. The National Electrical Code (NEC) specifies the requirements for overcurrent protection in branch circuits. The NEC requires that each branch circuit be protected by an overcurrent protection device that is sized to protect the conductors of the circuit. The ampacity of the conductors must be equal to or greater than the rating of the overcurrent protection device. The NEC also specifies the types of overcurrent protection devices that are permitted for use in branch circuits. Circuit breakers and fuses must be listed and labeled for the intended application. The NEC also requires that overcurrent protection devices be readily accessible and properly maintained. Circuit breakers should be tested periodically to ensure that they are functioning properly. Fuses should be replaced when they blow. In addition to the NEC requirements, local building codes may also specify requirements for overcurrent protection in branch circuits. It is important to consult with the local building department to ensure that all applicable requirements are met. When designing and installing branch circuits, it is important to consider the following factors. Firstly, the load requirements of the circuit. Secondly, the ampacity of the conductors. Thirdly, the type of overcurrent protection device. Fourthly, the accessibility of the overcurrent protection device. and fifthly, the local building code requirements. By carefully considering these factors, you can ensure that branch circuits are properly protected from overcurrent and that the electrical system is safe and reliable. The importance of service equipment and service disconnects needs to be mentioned. Service equipment and service disconnects are essential components of an electrical system that provide a means to safely disconnect the electrical service to a building or structure. Service equipment is the main control and protection point for the electrical system. It typically includes the service disconnect, overcurrent protection devices, and metering equipment. The service disconnect is a switch or circuit breaker that allows the entire electrical service to be disconnected from the utility power supply. Overcurrent protection devices, such as circuit breakers and fuses, protect the electrical system from damage caused by overcurrent conditions. Metering equipment measures the amount of electrical energy consumed by the building or structure. The service disconnect is typically located at the point where the service conductors enter the building or structure. It must be readily accessible and clearly labeled so that it can be easily located and operated in an emergency. The service disconnect must be capable of disconnecting all ungrounded conductors simultaneously. The National Electrical Code NEC specifies the requirements for service equipment and service disconnects. The NEC requires that service equipment be rated for the available fault current at the service entrance. The available fault current is the maximum amount of current that could flow in the event of a short circuit or ground fault. The service disconnect must be rated to interrupt the available fault current. The NEC also specifies the types of service disconnects that are permitted. Service disconnects can be either switches or circuit breakers. Switches must be horsepower rated and suitable for use as service equipment. Circuit breakers must be inverse-timed circuit breakers and suitable for use as service equipment. The NEC also requires that service equipment be properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. In addition to the NEC requirements, local building codes may also specify requirements for service equipment and service disconnects. It is important to consult with the local building department to ensure that all applicable requirements are met. When selecting and installing service equipment and service disconnects, it is important to consider the following factors. Firstly, the available fault current at the service entrance. Secondly, the ampacity of the service conductors. Thirdly, the type of service disconnect. Fourthly, the accessibility of the service disconnect. And fifthly, the local building code requirements. By carefully considering these factors, you can ensure that the service equipment and service disconnects are properly sized and installed and that the electrical system is safe and reliable. Furthermore, let's discuss wiring methods and materials for electrical systems. Wiring methods and materials are essential components of an electrical system that provide a safe and reliable means to conduct electrical current from the source to the load. The National Electrical Code NEC specifies the requirements for wiring methods and materials. The NEC recognizes a variety of wiring methods, each with its own set of requirements. Some of the most common wiring methods include: firstly, rigid metal conduit RMC, secondly, intermediate metal conduit IMC, thirdly, electrical metallic tubing EMT, fourthly, flexible metal conduit FMC, fifthly, non-metallic conduit PVC, sixthly, cable tray, seventhly, armored cable AC, eighthly, metal clad cable MC, and ninthly, non-metallic sheet cable NM. Rigid metal conduit RMC is a heavy-walled metallic conduit that provides excellent physical protection for conductors. It is typically used in applications where there is a high risk of physical damage. Intermediate metal conduit INC is a thinner-walled metallic conduit that provides good physical protection for conductors. It is typically used in applications where there is a moderate risk of physical damage. Electrical metallic tubing EMT is a thin-walled metallic conduit that provides limited physical protection for conductors. It is typically used in applications where there is a low risk of physical damage. Flexible metal conduit FMC is a flexible metallic conduit that allows for movement and vibration. It is typically used in applications where there is a need for flexibility. Non-metallic conduit PVC is a non-metallic conduit that is resistant to corrosion. It is typically used in applications where there is exposure to moisture or corrosive substances. Cable tray is a support system for cables. It is typically used in applications where there are a large number of cables. Armored cable AC is a cable with a metallic sheath that provides physical protection for the conductors. It is typically used in residential wiring. Metal-clad cable MC is a cable with a metallic sheath that provides physical protection for the conductors and also provides a grounding path. It is typically used in commercial and industrial wiring. Non-metallic sheath cable NM is a cable with a non-metallic sheath that is commonly used in residential wiring. The NEC specifies the types of conductors that are permitted for use in each wiring method. Conductors must be sized according to the ampacity of the circuit and the voltage drop requirements of the NEC. Conductors must also be insulated to protect against electrical shock. The NEC also specifies the requirements for installing wiring methods. Wiring methods must be supported and secured in accordance with the NEC. Conductors must be protected from physical damage. Wiring methods must be properly grounded. In addition to the NEC requirements, local building codes may also specify requirements for wiring methods and materials. It is important to consult with the local building department to ensure that all applicable requirements are met. When selecting and installing wiring methods and materials, it is important to consider the following factors. Firstly, the environment in which the wiring will be installed. Secondly, the risk of physical damage. Thirdly, the ampacity of the circuit. Fourthly, the voltage drop requirements. And fifthly, the local building code requirements. By carefully considering these factors, you can ensure that the wiring methods and materials are properly selected and installed and that the electrical system is safe and reliable. The role of the utility company when dealing with electrical installations is important to note. The utility company plays a crucial role in the electrical system, providing the electrical power that is used to operate homes, businesses, and industries. The utility company is responsible for generating, transmitting, and distributing electrical power to its customers. The utility company also maintains the electrical grid, which is the network of power lines and substations that transmits electrical power from the generating stations to the customers. The utility company has specific requirements for connecting to the electrical grid. These requirements are designed to ensure the safety and reliability of the electrical system. The utility company typically requires that all electrical installations be inspected and approved before they are connected to the grid. The utility company may also require that certain types of equipment be installed, such as surge protectors and ground fault circuit interrupters (GFCIs). The utility company also has requirements for metering electrical usage. The utility company installs meters to measure the amount of electrical energy consumed by its customers. The utility company uses this information to bill its customers for their electrical usage. The utility company also has programs to help customers conserve energy. These programs may include rebates for energy-efficient appliances and weatherization assistance. The utility company also provides information on how to use electrical energy safely. The utility company provides information on how to prevent electrical shock, how to use electrical appliances safely, and how to respond to electrical emergencies. In addition to the utility company's requirements, local building codes may also specify requirements for electrical installations. It is important to consult with the local building department and the utility company to ensure that all applicable requirements are met. When working with electrical installations, it is important to follow all safety precautions. Electrical work can be dangerous, and it is important to take steps to protect yourself from electrical shock. Always turn off the power before working on electrical equipment. Use insulated tools. Wear rubber gloves and shoes. If you are not comfortable working with electrical equipment, hire a qualified electrician. By following these safety precautions, you can help to ensure that electrical work is performed safely and reliably.